You can consider these notes on potential energy. So we've looked at work, we've looked at power, we've looked at kinetic energy, right?
Yep.
EK equals 1/2 mv squared, right?
Yep.
Power equals work divided by time. Work equals force times distance.
Yep, you got it, boss.
Okay. So let's talk about
That was good.
potential.
Anyways, really good.
Johnny, I'm kind of stalling the time here while everyone's getting themselves ready, loose leaf out, pencils out, that kind of stuff. That's what I'm doing right
Are you
now.
writing these?
Just kind of talking, filling space, not really saying
You
anything.
get 3 like this.
But
or
very soon I will say important things.
You get 3 like this or 3 like this.
Do you actually?
Yeah.
Trying to get into Google. Okay, so now potential energy could be gravitational, but it could also be chemical or that type of thing. We're going to deal mainly with gravitational potential energy. Chemical potential energy, that's for down the hall. Okay, so now if I recall correctly, these were transferred over from a PowerPoint, so that's why I have all these boxes, because they're hiding stuff. Okay, so vertical, and again, as always, please don't write everything down. Let's see what's underneath here. What do I have to do to get this to go away? Oh, the work done in lifting the mass at vertical distance d or h is stored inside the body as increased potential energy or increased gravitational potential energy, sometimes known with the letter U. U is used for gravitational potential energy, or UG, U gravitational. I tend to use U because that's kind of what I was taught. But if you prefer, if you want to use EP, I am bilingual. Right? Energy potential. If that works for you, if that makes more sense, then you go right ahead. Some textbooks I've seen also PE, potential energy, right? So, I mean, there's various ways of saying.
I can't believe you're going to use me.
Huh?
I can't believe you're going to use me.
You use you. Oh. Okay.
Them boo.
Yes. Okay. Do you need to write that down?
I don't know.
We're just setting the groundwork here, right?
Dustin is pretty sure on it all.
What am I writing down?
I don't know. I don't think there's anything there, right?
Yeah.
Just, oh yeah, okay. Gravitational potential energy, right? As you go up. Okay. Remember, W equals FD. I'm deriving here. Since F is equal and opposite to FW, mg, like the applied force is opposite the weight force, right? D is sometimes represented with H for height, so W equals FD becomes potential energy U equals mgh. That's how it's pronounced. Right? Gravitational potential energy is mass times gravity times height. The higher it goes, the greater potential energy. The more mass it has, the greater the potential energy, right? All of that work done is transferred into gravitational potential energy. When you're lifting weights down in the weight room, right? You're doing work, you're burning calories, you're lifting things, right?
Yep.
What if, are you doing work when you're like lowering the barbell?
Negative work. I don't know.
Well, if you didn't lower it slowly, right? It'd be going a whole lot faster, so I think you're doing work. Although the F is in the opposite direction from the distance, the displacement, isn't it? Let me think about that. Okay, let's say we've got a 5 kilogram ball, cannonball, something or other, right? It's on an 8 meter high ledge. Okay? This one you might want to jot down. This is a good sort of example. I'll give you a second. At that 8 meter high height, we would say that the potential energy, 5 times 9.8 times 8, it would have 392 joules of potential energy, right? Just stored in the object, just sitting there ready to do work.
Yes.
BS or PS?
Yeah.
Oh, yes.
PS.
You said BS. I'm like, really? You're calling me on that?
PS, Mr. Bennett. You taught us lies this whole unit.
Wouldn't it be something, eh? If a teacher just stood up here, just made up formulas, this is how you do this is how you do that, and it was all a big lie at the end.
Oh, that one was recorded though.
That one was recorded.
Okay, wait.
Inverse teacher burn.
I can see what you're saying.
Oh yeah?
We don't know.
Oh, that's right.
So, like, essentially, to us, it is what you do.
Oh, so you'll never know if what I'm telling you is the truth or not.
When you hey guys, take out the formula F equals HWPOZ, and we're like, what is that?
Interesting.
Like, teachers are talking about.
How much kinetic energy does it have when it's sitting there on that ledge? No. Kinetic. It has zero, right? It has zero kinetic energy. It's just sitting there, right? And so the total ET, you know, of phone home fame.
That's really funny.
I'm glad you enjoyed it.
What does the T stand for?
Total energy, ET. Total energy would be EK plus U, right? The total energy would be the 0 plus the 392. It's got 392 joules made up of potential and kinetic. Is it too small for you, Rep?
Yeah, DJ thought that J was point.
Oh, guys.
Does that help?
I have
Okay.
88 vision, and I'm farsighted. I can count how many stripes.
Now let's say it's at the 3 meter mark. How much potential energy does it have?
Hey, Riley. What? No.
No, it shouldn't have the same amount. Oh, it's only got 147 because it's at a height of 3. So even though now it's got kinetic energy, Brett, you're right. But even though it's now moving, it still has potential to go faster.
Yes.
Right? So it's at a height of 3, so 5 times 9.8. It still has 147 joules of potential energy.
That's stupid.
Well,
Well, I
what
think
makes
it's
your
science.
How much
Science.
is this gonna be?
No.
This is madness.
No.
Does it have kinetic energy?
I don't think so.
Yes, it does. But how do we find that, Cassie?
Some kind of formula.
Okay. What's the formula for kinetic energy? We've done already last week.
Kinetic energy.
1/2 mv squared,
Yes.
right?
Divided by 2.
Where'd you get the? Or-
Oh, never
MV
mind.
squared divided
You
by
said
2.
1/2.
mv squared over 2, same thing. Right? Same thing. Now,
And manganese.
we could figure out how fast it's going. Remember our old friend VS squared equals VI squared plus 2AD? Well, I'm just showing you what's going on here. Why do I use 5 for my distance?
Because it fell 5 meters.
Because it fell 5. That's right.
Thank you.
Right? It accelerated at 9.8, minus 9.8, I guess, for 5 meters. So it has a speed of 9.9
You don't know.
meters per second.
You're gonna
Don't-
give us some music.
Okay. It's moving at 9.9. Now we're going to use that kinetic energy formula, and we're going to get EK equals mv squared over 2. We're going to get 245 joules of kinetic energy. So it's got some potential, and it's got some kinetic. Is the total still the same? Was it 392? Is that what it was?
Yeah.
Is the total still 392?
Why do we have to do this?
Ah, because I want to show you that the total remains the same. Right? The total
Oh, add
does,
them up.
because energy must be conserved, right? Because I'm trying to find the total energy. Now, could we have used this idea to solve over here?
Probably.
Oh, yeah.
Right? Like I could have taken ET as 392, subtract the 147 to get the 245, and then put it in here to solve for the speed, right? I don't need to do it this way. So you can sort of, what I'm saying is you can go this way, or you can go that way.
You just want to show us first.
Right. Okay, because energy must be conserved. The number one rule is energy must be conserved. Okay?
What were you asking for in the first place?
I didn't really ask for anything. I'm just showing you what's happening. I haven't actually asked a question. I'm just really what I'm showing you is that momentum or energy is conserved. Now, what about when it hits the ground? That's the next step.
The energy goes to potential energy.
All right, so there's the three things, the lines you just wrote. So when it hits the ground, right? Oh, sorry, hang on, before we get there. What does this mean, delta U?
The change.
Change in potential, final minus initial. The change in potential is minus 245, 147. 147 minus 392, minus 245, right?
Why, wait,
I'm just showing you what's happening. I'm not asking you a question. I'm not asking you to solve for anything.
but how is the 147?
That's the final, because it went from way up there, top, to down here, right?
Here.
So right, but that's for the.
This is the final position, Talia, right here.
For it land.
No, I misspoke. We haven't landed yet. Final position, initial position, right? What would be the change in kinetic energy?
400. Oh, what? Oh, because it's
Final minus initial, right?
Yep.
So you'll notice that for every joule of potential energy lost, the object gains a joule of kinetic energy. Energy is always conserved. That's what I'm trying to get at here.
okay.
Let me write this down.
Energy is conserved.
The
Okay.
entire
So-
band blast is going to move to she's in cuts back.
Oh well. Hi. Thank you so much for bringing that up. Somehow we get time on. Oh, let's move
I
on.
read all the books.
Total energy is the same at all times. There is conservation of energy, and as an object moves, the changes in potential and kinetic are equal and opposite. So those are some key ideas,
No, don't.
right? The total energy is the same at all times, and the changes are equal and opposite. Well, pretty straightforward, I think, right?
Yeah. Are equal and opposite.
I get a feeling we might be ready for the sample stuff here. Am I right? Oh yeah, we are. Okay.
What else do you have?
All right, so here we have. Now, I remember growing up watching Rocky and Bullwinkle.
No, I
Probably beyond your. Yeah, you may have seen them a little bit. So Rocky, the 1 kilogram flying squirrel, is initially 10 meters up in a tree. He jumps down to the ground. Find his total energy at the start and at all times. Okay, so his total energy at the start in part A,
It'd be the same.
it's all potential. How come?
Because
He's not moving, right? He's initially 10 meters up in a tree. So that would just
Is that?
U equals mgh. He's 1 kilogram. Gravity is 9.8, and the height is 10. Oh, this is easy.
are we ever gonna do this on like a different planet so the gravity's like?
No, that would be simple. 98 joules. That would be his total energy start, and his total energy for the entire trip, I guess, right?
Yep.
I guess we could say ET is 98. Find his velocity after he's fallen 6 meters. Now, we could do that whole VF squared thing and all that, but let's do this from a sort of a conservation of energy standpoint.
Okay.
Okay? So, we're going to say ET, total energy, it's kind of like net force, right? Total energy is going to be EK plus U, and again, there's that weird thing, like why is it not EK plus EP? I have no answer for that. Well, it's like, kinetic energy plus potential. Like, if this is kinetic energy following the same naming system, it should be EP, should it not?
Yeah, I don't
Guess
know.
so.
But I use U,
Did
Deal with it.
places use you or is it just you?
I don't know. I've only been with me.
just what thing?
Is it just you?
Oh!
I thought it was a good one.
You guys have spent way too much time with me.
What am I gonna do?
When you start making Bennett jokes on your own, yeah, you're in rough shape. Okay, so the total is 98. Oh, after he's fallen 6 meters. So if he's fallen 6 meters, he's 4 meters from the ground, right?
Yes.
So EK plus MGH. Can we do it like this? Is that okay? Or you want me to do this separate?
No, I don't know what to do.
You want to do it separate?
Well, it'd be the same thing.
Okay.
No, why can't you not use the other way?
It would be the same thing.
It's the same.
It's the same thing.
Because it equals.
Yeah.
No, because
It's
you're.
okay. You can. No. Well, all I'm saying is you would do U equals MGH, so there'd be 1, 9.8, but now the height is 4, right?
Well,
So 9.8 times 4 is 2, 4, 6, 8, 39.2. Right? If you want to do this work over here, go right ahead. Which is what I was trying to do before. So that's going to be 98 minus 39.2.
40 of minute. Why did it be minus? Oh, never mind. Never mind.
Which means that our kinetic energy, what was the amount, Brett? 56 something? 58.8 joules. Right? No, but it actually asks for the velocity, right? Okay, so now we're going to say EK is equal to mv squared over 2. The EK is 58.8. Rocky's 1 kilogram, V squared over 2. So V is equal to, now can you do this math in your head? Like not the arithmetic, but can you do the rearranging in your head? You should be able to at this point, grade 12. So that's going to be 2 times 58.8, all over 1, I guess, right?
Yep. 117.6.
Did you take the square root?
The square root is 10.8.
10.84. That sounds like the more familiar number. So it's just an alternate route to that answer from a conservation of energy standpoint. Okay? Did we complete the problem? I think so.
What was it? 10.8?
10.84 meters per second. 2 kilogram ball is launched. Don't mock me, Riley.
No, I was just saying. It's just saying.
2 kilogram ball is launched at ground level at 50 meters per second straight up. Find the total initial energy. Find the height of rise using energy. Find the EK when it's risen halfway off the ground. And find the velocity when, oh, so much work.
What? You just said that?
Yeah, I can say that. You know how many times I've done this question, Johnny? No.
But hey, this will be the
I
last
guess
time.
I know.
18.
You know, you and I,
No,
you guys,
60 something.
okay. 2 kilogram ball launched at ground level at 50 meters per second straight up. Find the total initial energy. So now at the start, now I know you guys always say, well, it's 0 because it's just sitting there. No, no, no. As it's being launched, right? So all the total energy at the start is all kinetic, right?
So it is moving.
Yes, mv squared over 2. 2 kilogram ball, 50 squared divided by 2. Are we going to need to bring Kleenex, Megan, for the cake party? Or, no? I thought I heard you said you were going to cry.
Oh, she's gonna cry.
It's her birthday then.
Oh, is it really?
Yeah, 2 cakes. Oh my.
Oh, okay, what's a good game?
That's why I thought I could take a cake and then I could just pretend it's a birthday thing because I had no time to celebrate a birthday this year.
Well, we'll celebrate Megan's birthday at the same time as we celebrate my teaching demise.
No, but I'm getting nervous. The attention's on me now.
So it's going to be 50 squared, right? 2,500 joules of total energy. That's 8. That's it for 8, right? Is it not?
Yeah, it's easy.
Okay, so how are we going to figure out how high it's going to go using energy?
I don't know.
Well, remember, as it goes up, the potential energy increases, and the kinetic energy decreases. And in fact, at the very peak, at the very top right there, the kinetic energy is gone to zero, and the potential energy is the total, is it not?
2,500.
Right? And so therefore, at the peak, the U value is 2,500. Does that not make sense? At the peak, at the very top, all of it stops moving, no kinetic energy. All of the energy is now potential, so it's 2,500. So we solve for H, right?
And that's because it stops moving.
That's when it stops moving, exactly. So U equals mgh, 2,500. Mass is 2, 9.8. We're going to solve for H.
What's the? Okay, never mind.
You okay?
I dropped my calculator.
Okay.
Not my water bottle.
Number 9.
Oh!
127.6? 127.6 meters. 2,500 divided by 2 divided by 9.8. What?
I could just multiply it back.
Yeah, that's
Is that not the same thing?
It's the exact same thing.
Use your math skills, you guys.
That's what I did.
Yeah. Oh, yeah. Divide by 19.6, right? Yeah. What? Okay. Now, what about the kinetic energy when it's risen halfway?
Oh.
Okay. Now, let's make a prediction here. Halfway up, Mervyn, do you think it would be half of 2,500 joules?
No.
Feels like maybe, right? But that v squared bothers me.
No, it's yes.
Is it gonna
No, it's yes?
It's gonna be a
No, it's yes.
No, it's yes.
Obviously.
Yes, we have no bananas.
No, yes.
It'd be a,
I don't know.
we're going to take 127.6 and we're going to divide by 2 because it's halfway.
What is AJ?
He gets migraine.
No, but I haven't seen him in this class. I haven't seen him at school. in like
63.8.
It's migraine.
If you find
Yeah, that's cool.
Right.
He has a lot of
Okay.
training. I haven't seen
So we found out the height, the halfway height. Okay, you guys, just let's try to refocus a little bit. Well, it's hard when everyone else is all distracted. So if we all make a commitment to refocus a bit here. Partly my fault because I tend to be like that. Yeah, I get that. So I'll try to dial it back a
It's gonna
bit.
be litter than 20.
Okay, so Megan has come up with a strategy. She said we can take the potential energy at that point. Is that what you're saying, Megan?
Yeah.
So she's saying take U is equal to mgh. Mass is 2, 9.8, height of 63.8.
Yeah.
1,250 joules. If that's all the potential, Mervyn was right. EK equals U plus EK. I guess it doesn't matter what order they go in. Total energy was 2,500. So I guess if you stop and you think about it, it makes sense that halfway up, it's used up half, exactly.
So why did you do that?
What do you mean?
Show.
Yeah, to prove it. Would the speed be,
I'm confused.
would the speed be 25? If it was launched at 50, would halfway up, would it be 25?
Yes. Yes.
How did you get that? Because it not be 1250.
It should be 1250.
Oh, yeah.
Yeah, I literally thought I was.
Well, maybe I made that mistake to see if you were listening.
Yep.
Classic teacher move.
Yes, you did.
Which,
We didn't do E.
oh yeah, we haven't done D. But now I'm curious. I'm curious to know how fast it's going right here.
25. Pass.
Would it be 25?
Pass.
No, I'm curious.
No.
You feel like what? Why do you feel that, Brad?
Mathematically, it has.
Is it because it's that v squared thing? It is slowing down, right?
Yeah, I think
So why would it be 25? How can we find it?
do the math.
Well, we'll just do the math, right? We're gonna go EK is mv squared over 2. It's okay. I can be curious and answer this question if I want.
It does ask to find.
The mass is 2. So it's basically the square root of 1250, is it not?
Which is 35.3.
Oh. What is it? 35?
35.35.
I'm here.
Nobody else.
I can.
Christine, are you saying something?
I said that as it gets higher, the rate is slowing down, speeds up.
So it's like this.
No, I disagree. It slows down at the same speed the whole time. It's minus 9.8 meters per second squared.
Acceleration.
But isn't that what the rate of slowing down is? It's because it's v squared. That's why. Okay? So yes, it's not exactly half.
Well, what the heck? Why?
No, that is not the answer. Yep. That is the answer for C.5, exactly. The velocity when it's risen 100 meters, well, I mean, really, did I not just answer D except I did it for, like, halfway?
But you didn't.
It's the same process, right? How would you do it for 100? You'd have to do this step.
Oh.
You have to put 100 in there. You would do this step, do the subtraction, and then do this. Would you not?
Mm-hmm.
Be the same thing, would it not?
Repent.
You want me to do it? And you guys like to follow the rules, don't you?
I'm a rule breaker.
Okay.
I don't care about my name.
1960?
Okay, we're trying to learn.
What's up?
Johnny. Physics right now.
I know.
Johnny.
The phone.
Conversation.
Talking about physics.
Oh my god.
540 for the EK?
That's what I got.
Johnny.
What's that? That's the only way to find this, right? If you're trying to find the velocity, you have to find the EK first.
Do I have that written?
We could do that too, yes. Yeah. We're dealing with things from an energy standpoint.
Wait, can I write this down?
Would you get the 6 out of March? Would you get the expert?
I'll probably say in the question, do it from an energy standpoint, because I want to know that you know this stuff.
Plus mu, or mu. I keep wanting to say mu.
We're trying to find the velocity now, right? So that's going to be the square root of half of 2. Oh, that's just going to be the square root of 540, is it not? Okay.
Is that the answer? It's not the answer. Oh, it's not.
One more.
Johnny, do you only pay attention when you kids?
Did we?
No, I ran out of room. I was just like, oh no.
Do you think you could try number 3 on your own? Oh, come on.
I bet you can. Do we ever do that?
You hit what?
Like when it's on the other side, then it's not like.
Oh.
Did we ever finish that?
Oh.
I don't remember.
Did we ever finish what?
Yeah, I
Yeah,
watched
we
the
did.
video to see if we could correct the clicker stuff.
3 kilogram mass is thrown upward at 30 meters per second. It rises to a maximum height and then lands on a 5 meter high ledge on the way down.
Oh.
Very good.
Who can just throw it?
Find the total energy, the maximum height of rise, and the velocity just as it lands on the ledge.
Energy, huh? You see?
Okay, I'll give you. Oh, it's 3:15 already.
Give us 15 minutes.
8 minutes.
Yeah.
Okay. I'll just silently do A here. Energy.
Oh, and then I just moved the rate after that. What did you do? Why would you equal?
Ah.
Wait, why would you equal EK? Stops moving at the top.
13, 15.
That's what he did last semester. Man, I have no explanation behind why. But so he's
Do it.
What am I doing?
No, keep going.
Oh!
Keep going.
But,
See?
Yeah, you
yeah. A little wild.
Actually, that number sounds familiar.
Like 45, 39. Just round it up.
45.9 meters?
I rounded it up.
That's so
Okay.
simple. I was overthinking it way too much.
Okay, so how do we do C? Velocity just as it lands on the ledge. So right here,
The ledge is 40.
basically you want to know how fast it's going when it's 5 meters high, right?
What?
So I think all we got to do is go U equals mgh. 3 times 9.8 times 5.
Dang it, I did do 5. It wouldn't be the change in, I'm not sure.
That's 147.
This is the third time that I did the first step.
Why? Was the potential energy, explain to me why the total energy and kinetic energy equal each other?
At the start, when it's launched, how much, it's right at ground level, how much potential does it have? 0. It has no height. All of its energy is kinetic.
Why do I not understand this?
When we're finding
Well, we're going to find how much potential it has here, right? And then we're going to subtract that. And that's going to give us, because at this point right here, it's got EK plus U, right? So we got to find the U. We know the ET. That's going to give us the EK.
Why don't you take the height up from the peak?
Can we take the height of the peak
And,
and use it as potential?
oh, so you're saying take 40.9 and
Is that potential, is that, no?
you try and see if we come up with the same answer. I think it's going to work. Hang on, I haven't finished.
Mervin says it didn't work. It doesn't work.
No? I'm not real sure I know what you're saying, but I kind of like your thinking.
Hey, can you finish the
Yeah, I'm trying here.
I know you are, but.
I know you are, but I got the silly 147.
I know you are, but what am I?
Smart.
The teacher.
Thank you.
This you got.
I know you are. Oh, I hated it when kids said that back in the day. I pushed something out because it was no one and I pushed over. I don't know. Some kids like 2 years younger than me. And they're brats.
No!
Thanks for still on.
What is happening?
The
You mean like up one, go up one. Like you know, down, 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 down. Yeah, put each day in front of the equal sign. Yeah, right. Yeah.
Oh my, I can already tell it.
I'm pretty sure it's 28.3
Actually, Tara, you don't know how much that pleased me to hear you say that.
Well, it's not even about 10.
Oh my god.
28.3?
Yes, sir.
Hold on, I gotta do it myself.
Excuse the interruption. I just wanted to let everyone know that